Thank you very much. So I will talk about the detection of illegal landfill. This is part of a European project called Perivallon, which involves 24 partners from 12 different countries of the European Union. We, as Politecnico di Milano, are involved as experts in the artificial intelligence, deep learning, and computer vision fields. The main objective of our work is to develop tools able to detect landfill through Earth observation and then perform more evaluation using drone images or, in general, drone data during in-site inspections. So far, we have produced a dataset for waste detection. It's called Aerial Waste. We have also developed a web tool used to annotate data and evaluate the model performances called Odin Web. We have developed a framework to train and evaluate deep learning models and a pipeline to analyze, to scale our deep learning models to large territories. And in general, we are doing a lot of research to exploit new architecture and techniques for the waste localization problem. First of all, the dataset. It's the most important part of the work. Aerial waste is publicly available on Zenodo. It's composed of remote sensing images of as of now, only the Lombardy region in Italy. These are either satellite images like World View or images taken from planes like AGEA and Google Earth images. All the images in the dataset contain an area of 210 meters by 210 meters. It is quite a large area, less than other images we have seen in previous works, because they are very high resolution images. For example, AGEA is 20 centimeters per pixel. WorldView is a bit lower quality, 30 centimeters per pixel. We have both binary and multi-class labels. In particular, the entire dataset is labeled for the binary classification problem. Roughly a third is for positive, so the image contains actual waste, while the other 2/3 do not contain waste. For the multi-class label, we have currently a little less than 1,000 images, divided between 17 classes. We have also some segmentation annotations. These are quite expensive to do, so we have very few. We only use them to evaluate the localization capabilities of our models. These are some examples from the aerial waste dataset. These are not the entire images. I just took a snapshot of the most relevant part. Should be about 10, 20 meters by 10, 20 meters. In the first image, we can see the black area are tires, while the white on the bottom part should be plastic. Here we have some rubble, and in the last one, there is a deposit of firewood. We have also trained a lot of binary models. This is what we use as a baseline and for our inference campaigns alongside ARPA Lombardia, which is the regional agency for environmental protection. We are using mostly a ResNet 50 base model and a feature pyramid network whose objective is to, let's say, mostly enhance the localization capabilities by extracting features at different scales. As you can see, it takes as input the output of the last 4 major blocks of the ResNet, and it combines them through concatenation, and the smoothing part is basically an upsampling. Finally, we have the classification head. It's a simple 2 fully connected layers. The performances are quite good. We are decently satisfied as of now. We have an 80-81% F1 score. Our main objective would be to get to, let's say, 90–95%. And to achieve this, we are employing we are doing a lot of research, mainly on the augmentation techniques, involving also hide-and-seek techniques and more traditional augmentation. We are testing other frameworks or models, such as Inception ResNet, Visual Transformer. We also recently tried a multiple instance learning approach, which is very promising. The model I showed you before is available on GitHub with the corresponding weights. Feel free to use them. Finally, we have the annotation tool, which is a major part of the work we have done so far. It's called Odin. It is again available on GitHub as a Python library. We are also developing a web tool. Currently, it's not publicly available, but hopefully it will be in the future. The main 4 components are the analyzer, which allows to evaluate the performances of the model on a more traditional way. So we are looking at metrics like F1 score, accuracy, intersection over unions, stuff like that. We have the comparator, which is an extension of the analyzer. It allows to compare, as the name suggests, 2 or more models. Then we have the visualizer, which allows to perform a more qualitative analysis of the performances. For example, the main approach will be a class activation maps and heat maps. And finally, but probably the most important part, is the annotator, which allows to annotate the dataset. We have used this a lot, and I cannot stress it enough how much it has been useful for our work. As I was saying, we have also the web interface for Odin called Odin Web. It offers the same functionalities and some more. Mainly, we have the map visualizer, which allows to visualize the performances of the model on larger scales, such as we have recently done an inference of a large area in the Lombardy region, and this allows to look at specific municipalities, for example. We are now going to see a bit of the interface in Odin Web with some data we have analyzed. In general, first of all, the analyzer. As you can see, we have, this is for the binary classification model, so we have a third, as I was saying, it's considered waste, the other 2/3 are not. And we can also look at other performances by clicking on the tab over there. This is part of the comparator. As I was saying, it's part of the analyzer. It allows to inspect the performances. We can select a single, let's say, a single metric. We can also look at the confusion metrics, either for a single model or for multiple models. Then we have the annotator. Again, in this case, as you can see, we can look at the image and then decide whether it contains waste or not in case of the binary problem. We also have, we call them properties. You can call them meta-annotation. Doesn't really matter the name, but it allows to, let's say, add additional informations that are useful for people who work in, for example, people who work in ARPA is asked to add this feature to, say, for example, the severity of the landfill, let's say, or the quality of the image overall. We can also take a look at the annotator for the multi-class multi-label and multi-class single label problems. In the first case, it allows to select multiple classes. In the second one, it allows to select only one. It is also possible to draw polygons on the image to annotate for instance segmentation or object detection. Finally, we have the map visualizer. As I was saying, this is taken from a recent inspection we had done in a Lombardy region. And in blue, you can see the municipality we are analyzing, and the various squares are images that our model has analyzed. it only highlights the images that have a confidence score higher than 0.2, and it's color-coded. So, for example, we mostly only take into consideration the red ones, and some of the orange ones as they have a higher confidence score. And it's, again, very useful to understand this. Also tells somewhat of a story where most landfills are. As you can see, they are the most, let's say, evident one, are located outside or on the border of the municipality and not actually inside of the city. Finally, we have also again, the visualizer. It is, this part is inside the annotator because it mostly makes sense on from a programming point of view. As you can see, it allows to, by clicking on the button, it allows to look at the predictions, which is the confidence score of the model, and also activate a layer which highlights the most relevant part extracted by the model. In this case, we are using class activation maps. It's standard class activation maps. It's not GradCam, but we are also trying this other technique. Here are a few of the next steps we will be doing in the future. First of all, we want to finalize the binary classification architecture. We have done a lot of research in the past months. We have a lot of techniques. I haven't shared much because of time constraints, but if you want to ask some questions, please do. We are now moving also towards the multi-class and multi-label classification problem, which is much harder because, as you probably know from satellite images, while a landfill can be easily detected, different type of waste are not so easily detected. There can be a lot of nuance about it. We are also working on drone data. In particular, we will our target will we want to identify specific target. One such example is asbestos slabs, which are, of course, extremely dangerous to the environment and human health. And this will mostly use 2D images because they are easily collectible, but we are also planning on using 3D point cloud data, either from a LiDAR sensor or extracted using structure from motion. And in general, more updates for aerial waste. In particular, we are planning one that will include more areas from different parts of Europe. There are partners from Greece, Romania, and Sweden who are collecting and annotating images. And we are also collaborating with the United Nations Development Program for the Guatemala region. These are some papers we have published regarding our work so far, so feel free to check them out. And this is all from me. Thank you for your attention, and if you have any questions, please do.
Thanks a lot.